Welcome to DAR Tutors for online and home tuition. Today we will delve into a fundamental topic in IB Chemistry Higher Level: reaction mechanisms. Understanding how a reaction occurs step by step provides insight into its rate and stereochemistry. In this video, you will learn about the mechanisms for two major classes of organic reactions. First, we will cover nucleophilic substitution reactions of halogenoalkanes, including the SN1 and SN2 mechanisms. Then we will explore electrophilic addition reactions of alkenes. Finally, we will look at electrophilic substitution reactions of benzene. The goal is to not only predict the products of these reactions, but also to fully describe the mechanisms, including transition states, intermediates, and the factors that influence which pathway is dominant. Let's begin with nucleophilic substitution. Our learning objective for this section is to be able to define the terms nucleophile and electrophile, and to describe the general nucleophilic substitution reaction. So, what are these key terms? An electrophile is an electron lover, a species that is deficient in electrons and can accept an electron pair. A nucleophile, on the other hand, is a nucleus lover, a species with a lone pair of electrons that can be donated. Halogenoalkanes are excellent electrophiles. The halogen atom is more electronegative than carbon, so the CX bond is polar. This partial positive charge on the carbon atom makes it attractive to nucleophiles. The halogen atom itself is a good leaving group, meaning it can depart as a stable halide ion. The general mechanism involves a nucleophile attacking the carbon, forming a new bond, and the carbon-halogen bond breaking, releasing the halide ion. So, a new bond is formed and an old bond is broken. Let's look at a specific example: the reaction of 1-iodo-propane with aqueous hydroxide ions. The hydroxide ion, with its negative charge, is an obvious nucleophile. It will attack the partially positive carbon atom of the Ci bond. The product will be propan-1-OL, with an iodide ion as the leaving group. This reaction is a classic example of nucleophilic substitution. In this scene, we've achieved our objective. We have defined electrophiles and nucleophiles, and we have seen a clear example of how a nucleophilic substitution reaction occurs. While the general reaction is simple, the actual pathway, or mechanism, is more complex. Carbon can only form 4 complete bonds at a time, so there are 2 main ways a bond-making and bond-breaking event can occur. These give rise to 2 distinct mechanisms. The first is the SN1 mechanism, which is a 2-step process. In this mechanism, the carbon-halogen bond breaks first to form an intermediate called a carbocation. Let's examine the SN1 mechanism for 2-bromo-2-methylpropane reacting with hydroxide. First, the carbon-bromine bond breaks. The bonding electrons go entirely to the bromine atom, which leaves as a stable bromide ion. This slow step, known as heterolytic fission, is the rate-determining step because it has the highest activation energy. The resulting intermediate is a tertiary carbocation, with a positive charge on the central carbon. In the second step, the carbocation, which is a powerful electrophile due to its empty p orbital, is rapidly attacked by a nearby nucleophile, such as the hydroxide ion. This fast step completes the substitution. The name SN1 indicates it's a substitution reaction. It's nucleophilic, and the rate-determining step is unimolecular, meaning it only involves one molecule, the halogenoalkane. Now let's consider the second mechanism. This mechanism provides an alternative pathway that bypasses the carbocation intermediate. This is the SN2 mechanism, a 1-step concerted process where bonds are broken and formed simultaneously. The learning objective is to be able to describe this mechanism, including the formation of a transition state. In an SN2 reaction, the nucleophile attacks the carbon atom from the opposite side of the leaving group. This is called backside attack, and it is crucial for proper orbital overlap. Let's look at the reaction of bromoethane with hydroxide. As the hydroxide ion approaches from the back, a partial bond starts to form. At the same time, the partial bond with the bromine atom begins to break. This fleeting high-energy state is called the transition state, or activated complex. It cannot be isolated. In the transition state, the carbon atom is simultaneously bonded to 5 other atoms: the incoming nucleophile, the leaving group, and its three original substituents. As the hydroxide carbon bond fully forms, the carbon-bromine bond fully breaks, and the bromide ion departs. The name SN2 signifies it's a substitution nucleophilic reaction, and the single, slow step is bimolecular, involving both the nucleophile and the halogenoalkane. This scene has shown the concerted SN2 mechanism and the formation of the transition state. You are now able to describe this one-step process. A key difference between the SN1 and SN2 mechanisms is their stereochemistry. Our objective is to distinguish between stereospecific and non-stereospecific reactions. The SN2 reaction is stereospecific. The nucleophile must attack from the back, causing the other groups around the carbon to flip, like an umbrella in a strong wind. If we start with a single optical isomer at a chiral carbon, we get a single optical isomer as the product. The configuration is inverted. Consider this chiral bromoalkane. The hydroxyl nucleophile can only attack from the back. This forces the methyl, phenyl, and ethyl groups to invert their positions relative to each other, resulting in a product with the opposite configuration. The SN1 reaction, however, is not stereospecific. It leads to racemization. Why? Because the carbocation intermediate is planar. Once the planar carbocation forms, the nucleophile can attack from either the top or the bottom face with equal probability. This means a racemic mixture of both possible enantiomers is formed in equal amounts, making the final product optically inactive. In this example, the chiral bromoalkane forms a planar carbocation intermediate. This intermediate can then be attacked from the front or back, leading to a 50-50 mix of the R and S enantiomers of the alcohol. This scene has shown how the mechanism dictates the stereochemical outcome. We have two competing mechanisms. The key question is, which one will happen? Our objective now is to identify the factors that determine whether an SN1 or SN2 mechanism is dominant. The two most important factors are the structure of the halogenoalkane and the nature of the nucleophile. Let's focus on structure first. A stable carbocation is crucial for SN1. Carbocation stability follows a clear trend. Tertiary is more stable than secondary, which is more stable than primary. Tertiary carbocations have three alkyl groups, which are electron-donating. These groups stabilize the positive charge through hyperconjugation by sharing electron density from their CH sigma bonds with the empty p orbital of the carbocation. This stabilization significantly lowers the activation energy for SN1. Now let's consider steric hindrance, which is a major factor in SN2. The backside attack required for SN2 cannot happen if there are bulky groups blocking the way. A methyl group has no steric hindrance, so SN2 is very fast. Primary halogenoalkanes have only one alkyl group, allowing for efficient backside attack. Secondary halogenoalkanes are more hindered, and tertiary halogenoalkanes are so crowded that an SN2 reaction is virtually impossible. The nucleophile strength also matters. SN2 reactions benefit from strong nucleophiles that can effectively push out the leaving group in one step. SN1 reactions are less sensitive to nucleophile strength because the carbocation is already formed in the slow step. Finally, the leaving group. For a halide to be a good leaving group, it must be stable as an anion. This correlates with bond strength. A weaker carbon-halogen bond is easier to break, leading to a faster reaction. The Ci bond is the weakest, making iodide the best leaving group. So, combining these factors gives us a clear picture. Tertiary halogenoalkanes react almost exclusively by SN1. Methyl and primary halogenoalkanes react almost exclusively by SN2. Secondary halogenoalkanes can go by either route, depending on the conditions. This scene has covered how structure, nucleophile strength, and leaving group determine the reaction mechanism. We now move to a new class of reactions: electrophilic addition. In this section, our objective is to describe the mechanism for the electrophilic addition of halogens to alkenes. Alkanes, with their carbon-carbon double bonds, have a high electron density due to the pi electrons. This makes them nucleophilic, meaning they are attracted to electrophiles. Consider ethene and bromine. While a bromine molecule, Br2, is nonpolar, the high electron density of the alkene's pi bond can induce a temporary dipole. This makes one bromine atom slightly positive and the other slightly negative. In the first slow step of the mechanism, the pi electrons attack the partially positive bromine atom. Simultaneously, the bromine-bromine bond breaks heterolytically, with the electrons moving to the more electronegative bromine. This forms a cyclic intermediate called a bromonium ion, which is a three-membered ring containing two carbons and a positively charged bromine atom. The second step is fast. The bromide ion, which is a good nucleophile, attacks one of the carbon atoms of the bromonium ion from the side opposite the other bromine atom. The three-membered ring opens and the final product, 1,2-dibromoethane, is formed. Evidence for this mechanism comes from its stereospecificity. The mandatory backside attack in the second step leads to a product where the two halogen atoms are on opposite sides of the molecule. This anti-addition is the characteristic outcome of this two-step mechanism. We have now met our objective by describing the mechanism. Now let's consider adding hydrogen halides to alkenes. The mechanism is similar to halogen addition, but with an important twist. Our objective is to learn Markovnikov's rule and apply it to predict the major product in the addition to unsymmetrical alkenes. The electrophile is the hydrogen halide, HBe. The hydrogen atom is more electronegative than bromine, so the HBr bond is polar, with a partial positive charge on the hydrogen. First, the pi electrons of the alkene attack the partially positive hydrogen of H. Simultaneously, the HBr bond breaks heterolytically, with the electrons going to the bromine. This forms a carbocation intermediate and a bromide ion. This step is the slow rate-determining step. Unlike the halogen addition, a cyclic intermediate is not formed. Instead, we have a linear carbocation. The bromide ion then attacks the carbocation to form the final product, a halogenoalkane. If the alkene is unsymmetrical, the hydrogen can add to either carbon of the double bond, leading to two possible carbocation intermediates and thus two possible products. For example, in the addition of HBr to propene, the p electrons of propene can attack the hydrogen of HBr in two ways. One pathway forms a secondary carbocation on the middle carbon. The other forms a primary carbocation on the end carbon. We know that a secondary carbocation is more stable than a primary carbocation due to hyperconjugation. A more stable intermediate means a lower activation energy for its formation and therefore a faster reaction. This leads to Markovnikov's rule. When a hydrogen halide adds to an unsymmetrical alkene, the hydrogen atom adds to the carbon atom of the double bond that already has the greatest number of hydrogen atoms. You can remember this as the rich get richer. The major product will be 2-bromopropane. Let's work through another example. Predict the major and minor products of the reaction between 2-methylpropene and HB. First, we look at the double bond in 2-methylpropene. The left carbon is attached to two methyl groups and no hydrogens. The right carbon is attached to two hydrogens. So, according to Markovnikov's rule, the hydrogen from HBr will add to the right carbon. This addition generates a tertiary carbocation on the central carbon atom. This is the most stable possible carbocation, so this pathway will be the fastest. A less favorable pathway would lead to a primary carbocation. The major product, formed from the tertiary carbocation, will be 2-bromo-2-methylpropane. The minor product from the primary carbocation would be 1-bromo-2-methylpropane. We have now successfully applied Markovnikov's rule to predict reaction outcomes. Our final topic is electrophilic substitution of benzene. The objective is to explain why benzene undergoes substitution rather than addition, and to describe the general mechanism. Benzene has a high electron density above and below the plane of its atoms from 6 delocalized pi electrons. This delocalization provides exceptional stability, known as aromatic stability. Because of this aromatic stability, benzene is reluctant to give up its pi electrons and lose this stability. Therefore, unlike alkenes, it will not react with weak electrophiles in addition reactions. However, benzene will react with strong electrophiles in a two-step substitution reaction. An electrophile, E+, replaces one of the hydrogen atoms on the ring. The general mechanism involves two steps. Step 1, the slow rate-determining step, involves the electrophile attacking the benzene ring. The pi electrons of benzene attack the electrophile, forming a carbocation intermediate. This intermediate is stabilized by resonance, with the positive charge delocalized across the ring. However, its formation still temporarily disrupts the aromatic stability, requiring a high activation energy. Step 2 is fast. A base in the reaction mixture removes a hydrogen atom from the ring. The electrons from the carbon-hydrogen bond move back into the ring, restoring the aromatic stability. This regeneration of the aromatic system is what makes substitution so favorable in benzene. We have now covered our objective. Let's look at some specific examples of electrophilic substitution reactions. Our objective here is to identify key electrophiles and the reactions that generate them. The electrophiles used in these reactions are often not stable enough to exist on their own. They are generated in situ, meaning they are formed right in the reaction mixture. Perhaps the most well-known example is nitration, which adds a nitro group to the benzene ring. The strong electrophile, the nitronium ion, NO2+, is generated by reacting concentrated nitric acid with concentrated sulfuric acid. The sulfuric acid acts as an acid, protonating the nitric acid, which then loses water to form the nitronium ion. Another important class of reactions are the Friedel-Crafts reactions. These use aluminum chloride, a Lewis acid catalyst, to generate an electrophile from a halogenoalkane or an acyl chloride. For example, in Friedel-Crafts alkylation, aluminum chloride reacts with bromoethane to generate a carbocation, CH3CCH2+. This carbocation then acts as the electrophile, attacking the benzene ring. The catalyst AlCl3 plays two roles. It helps form the electrophile, and it assists in the deprotonation in the second step to regenerate the catalyst and the aromatic system. We have now identified some key electrophiles. We have now covered the key concepts and mechanisms of nucleophilic substitution, electrophilic addition, and electrophilic substitution. Let's recap what we've learned. We started with nucleophilic substitution, exploring the SN1 mechanism, which is a two-step process involving a carbocation intermediate and racemization, and the SN2 mechanism, which is a one-step process involving a transition state and stereospecific inversion. We saw that tertiary halogenoalkanes favor SN1 due to carbocation stability, while primary halogenoalkanes favor SN2 due to lack of steric hindrance. Next, we moved to electrophilic addition to alkenes. We saw that the high electron density of the alkene double bond makes it nucleophilic. Halogens add via a cyclic bromonium ion intermediate, leading to anti-addition. Hydrogen halides add via a linear carbocation intermediate, with the major product determined by Markovnikov's rule based on carbocation stability. Finally, we covered electrophilic substitution in benzene. Benzene's aromatic stability makes substitution, not addition, the preferred pathway. This involves the formation of a resonance-stabilized carbocation with strong electrophiles generated in situ. To solidify your understanding, let's work through some IB-style practice questions. As you tackle these problems, remember the principles of carbocation stability, steric hindrance, and stereochemistry. Question 1. Which halogenoalkane reacts fastest in a nucleophilic substitution reaction via an SN1 mechanism? A. 1-bromobutane. B. 2-bromobutane. 2-bromo-2-methylpropane. D. bromoethane. Take a moment to think about it. The SN1 mechanism proceeds via a carbocation intermediate, and the rate is determined by carbocation stability. The more stable the carbocation, the faster the reaction. A primary halogenoalkane forms a primary carbocation, a secondary forms a secondary, and a tertiary forms a tertiary. As we know, tertiary carbocations are the most stable. 2-bromo-2-methylpropane is a tertiary halogenoalkane, and therefore it forms a tertiary carbocation. The correct answer is C. Question 2. Draw the mechanism for the reaction between S1 iodoethane and ethoxide ions, CH3CH2O-. Include the stereochemistry of the product. Pause the video here and try to draw the complete mechanism. First, we need to analyze the reactant. 1-iodoethane is a primary halogenoalkane. Primary halogenoalkanes undergo SN2 reactions. Second, ethoxide is a strong nucleophile, also favoring SN2. The reaction is a single-step concerted process. The ethoxide will attack the carbon bearing the iodine from the backside. The mechanism should show curved arrows, one from a lone pair on the oxygen of ethoxide to the carbon, and another from the carbon-iodine bond to the iodine, showing the leaving group departing. A transition state should be included in square brackets, showing the partial bonds forming and breaking. The carbon in a trigonal planar-like geometry. The stereochemistry of the product, R1-ethoxyethane, must show inversion of configuration. This complete diagram shows the backside attack, the transition state, and the resulting inversion of configuration at the chiral center. This is a perfect example of a stereospecific SN2 reaction. Question 3. Predict the major product of the reaction between 1-butene and HBD. Pause and consider the structure of the alkene. Is it symmetrical or unsymmetrical? 1-butene is an unsymmetrical alkene. Therefore, this reaction will follow Markovnikov's rule. We need to identify the carbons of the double bond and count the hydrogens on each. The first carbon of the double bond has 2 hydrogens. The second carbon has 1 hydrogen. According to Markovnikov's rule, the hydrogen from HBr will add to the carbon with more hydrogens, which is the first carbon. This addition generates a secondary carbocation on the second carbon. A primary carbocation on the first carbon would be much less stable. The more stable secondary carbocation will react with the bromide ion to form the major product, 2-bromobutane. This application of Markovnikov's rule is key to predicting the outcomes of electrophilic addition. The major product is 2-bromobutane. The minor product, formed via the less stable primary carbocation, would be 1-bromobutane. Question 4. Describe the mechanism for the bromination of benzene. Remember, this is not an electrophilic addition. This is electrophilic substitution. First, we need to generate the strong electrophile, the bromonium ion. We do this in situ by reacting benzene with bromine and a Lewis acid catalyst like iron 3 bromide. The iron 3 bromide reacts with bromine to form the electrophile Br+ and a complex anion, Phe-bar4. Step 2 is the slow, rate-determining step. The pi electrons from the benzene ring attack the electrophilic bromonium ion. This forms a resonance-stabilized carbocation intermediate, which is often called the sigma complex or arenium ion. This step temporarily breaks the aromaticity of the ring, which is why it has a high activation energy. Step 3 is fast. The complex anion, Phe-bar4, acts as a base. It deprotonates the carbocation intermediate, removing a hydrogen atom. The electrons from the CH bond flow back into the ring, restoring the aromatic stability. The products are bromobenzene, hydrogen bromide, and the catalyst iron 3 bromide, which is regenerated. Question 5. A racemic mixture of a chiral halogenoalkane reacts with aqueous hydroxide. Is the reaction more likely to be SN1 or SN2? Justify your answer. Pause and think about what a racemic mixture implies about the starting material. A racemic mixture is a 50-50 mix of 2 enantiomers. For a reaction to start with a racemic mixture, the halogenoalkane itself must be chiral. Remember the key outcome of SN1 and SN2 reactions when starting with a single optical isomer at a chiral carbon. An SN1 reaction with a pure enantiomer leads to racemization, producing a 50-50 mixture of both enantiomers. An SN2 reaction with a pure enantiomer leads to a single enantiomer with inverted configuration. Since the starting material is already a racemic mixture, the stereochemical outcome of the reaction will also be a racemic mixture. However, this does not tell us the mechanism. Both an SN1 reaction starting from one enantiomer and an SN2 reaction starting from the other enantiomer could lead to a racemic product mixture. We need more information, such as the structure of the halogenoalkane, to make a definitive prediction. The structure is the most important factor in this case. We hope this comprehensive review of reaction mechanisms in IB Chemistry HL has been helpful. We've covered the crucial SN1 and SN2 mechanisms, electrophilic addition to alkenes, and electrophilic substitution of benzene. Understanding these mechanisms is not just about memorizing steps. It's about developing the analytical skills to predict and explain chemical reactivity. We've shown how factors like carbocation stability and steric hindrance govern which pathway is followed. Thank you for watching. For more expert tuition in IB, A-Level, and IGCSE chemistry, please contact DAR Tutors. You can visit our website or reach out via email. Our team of experienced tutors is ready to help you achieve your academic goals.